Hello, my name is Arman Iranfar from Embedded Systems Laboratory, EPFL Switzerland. In this presentation, I will introduce ReLearn, which is a robust machine learning framework for multimodal stress detection from physiological signals in presence of missing data. As you know, stress is known as a major issue of modern societies, causing health problems. Fortunately, these days we have machine learning techniques and embedded systems that made it possible to have continuous monitoring and detection of stress by means of tracking physiological signals such as electrocardiogram or electrodermal activities and respiration. However, working with these physiological signals is not a piece of cake. And one major problem is that for machine learning, we require clean data, but these signals usually have some problems, such as including noisy data or having missing values or outliers that strongly affect the accuracy of machine learning algorithms. There are a few conventional techniques that try to address these problems. For example, we have filtering, ignoring the missing data, or data imputation. However, these techniques have their own problems. For example, if the imperfect part of data is discarded, then there would be no prediction actually available for that segment. Also, for example, ignoring a part of data means that we have less data available, which is actually very important and critical for machine learning based solutions. Therefore, we need a more comprehensive solution to deal with these problems, I mean outliers and missing data, and that's what we address through the ReLearn framework. So let's see what ReLearn is and how it works. First, physiological signals go through a pre-processing stage where the training data is obtained, and this data includes missing values and outliers, and the purpose of the rest of the framework is to deal with these issues. So we propose to pass this part of data through a feature pruning stage where we can split the dataset to two separate parts, one without any missing values and the other including missing values. Then with the data that does not have any missing values, we train a machine learning feature selector, an imputer, and an outlier detector. By using these training models, then we are able to clean the other part of the training data so that there is no missing values and outliers anymore in that part of data. Then we can recombine these two datasets and have complete training datasets, but this time without any missing values. So now that we have a much larger and cleaner training dataset, we propose to retrain the feature selector, the imputer, and the outlier detector to have more accurate models. Finally, the output of these models can be used to train our main classifier. At inference, what we do is that the unclean test data can pass through these models, providing clean data, and then we can provide the predictions through our classifier. In the preprocessing stage, we extract parameters from the physiological signals, and then we extract the features. Then the data is divided into separate non-overlapping sets for training and testing. As I already mentioned, the training data at this stage includes outliers and missing values. And in the feature pruning stage, what we do is to remove a feature if more than X% of its samples are missing. Then the remaining data is split into two parts, one that still contains missing values and the other one that does not have any missing values. In the next stage of the framework, we first work with the training data that does not have any missing values. So we use isolated forest algorithm, which is a machine learning in-layer detector. Then we have the recursive feature elimination technique with random forest as the base classifier uh, that is used for selecting the most significant features. Next, we use multivariate imputation technique with Bayesian ridge algorithm as the baseline regressor to learn how to impute a feature's value from the existing data. Finally, we apply the inlier detector to make sure outliers are carefully handled. Then it's time to handle the missing values and outliers on the second part of the training data, the one that included missing values and outliers. For that, we can simply apply the train models that we just obtained and provide a cleaner data set. The outcome then could be would be the data that does not have any missing values, and we can now concatenate these two sets to obtain our final clean data set for training the extreme gradient boosting algorithm as our main classifier for this work. Uh, Before diving into the results, I briefly explain the experiment protocols and our stress database. We had 95 subjects, including males and females, that participated in an experiment where they were divided into two groups. One of them were performing the stress task, and the other one doing the control tasks. During the experiment, we collected physiological signals from the subjects, including ECG, PPG, EDA, and respiration. And finally, our database included 94 physiological features in the time and frequency domains extracted from time series in segmentation windows of 1 minute. So let's look at some results. The first important aspect of ReLearn that we need to study is the effect of the threshold value we use for feature pruning stage. As you can see in this figure, with lower threshold values, although the mean cross validation accuracy is good enough, it has a large variance, standard variation actually. The reason lies in the fact that more features and samples are dropped with a small threshold, and although we have a cleaner data set, the amount of data is not sufficient for machine learning algorithms. Then, if you look at the other end of the graph, you see that the standard deviation decreases, which is good, but we have lower accuracy, and that's actually because with larger threshold, less features and samples are dropped, meaning that now we have more data, but they are not clean enough. As you see in the middle of the figure, we have a better trade-off where we have enough data and at the same time they are sufficiently clean. We have compared ReLearn with several traditional remedies used to deal with missing data, such as dropping missing values or using mean value or last values as the data imputation technique and so on. As you see in both cross-validation and inference, the mean and standard deviation of prediction accuracy have improved through the proposed framework. And more importantly, if we just consider the part of the data that contained missing values, now ReLearn is able to improve the prediction accuracy compared to the other imputation techniques. So let me conclude this presentation. Here we discussed and talked about the importance and challenges of having clean data to train machine learning algorithms for stress detection from physiological signals. We introduced ReLearn as a robust machine learning framework that addresses missing values and outliers existing in physiological signals. Compared to the conventional imputation techniques, ReLearn could improve the prediction accuracy by at least 26% for missing samples. Thank you very much for your attention.